Hi, my name is Richard Keach. This talk is called Why Zero Carbon Living is Economic, otherwise known as the amazing benefits of efficiency and electrification. Okay, for context, renewable energy and energy efficiency are my professional life. I work at NHA Consulting and my freelance outfit, New Energy Thinking, where I do home energy efficiency work. And you can find me on Facebook at My Efficient Electric Home. Let's start with efficiency thinking. My favorite definition of sustainability is from Paul Hawken, the American environmentalist, who says that sustainability is aligning with natural forces, or at least not opposing them. That evokes the jiu-jitsu style idea of achieving significant outcomes with very little effort by using your opponent's weight in your favour. It's also found in the idea of a child's swing, where you can achieve significant output in terms of the motion of the swing if you time your pushing right, but if you try to make the swing go much faster or slower than its natural frequency, then you need much more energy to do that. So applying this idea to efficient homes, let's start with what it's not. A naive view of efficiency is that it necessarily involves a trade-off, giving savings but getting less in the process. An example would be taking shorter showers or turning the lights off. But in reality, efficiency done well is not like that. Efficiency done well is a win-win-win. And I'll describe that in terms of what I call the leaky bucket problem. So a way to think about homes and the way they're heated and cooled is that homes are like leaky buckets. Heat flowing through homes is like water flowing out of a leaky bucket. In this analogy, the bucket has structure, water and depth, and those three things correspond in this analogy. The bucket structure is like a home's thermal envelope, the water is like the heat energy, and the depth of water in the bucket is like the temperature we're trying to achieve. The implications of this thinking are that it firstly underscores the absurdity of trying to fill faster instead of stopping a leak. It can help change your expectations around homes when you start thinking like this. It helps explain how heat flow is variable and controllable, that a law of diminishing return applies, and that good performance is impossible without fixing the bucket. So with this line of thinking, it's appropriate to patch the biggest hole first. And let me explain that in terms of my own experience, fixing my own leaky bucket, shall we say. This is my house in suburban Melbourne, Australia, and 2006 was the last year before I made significant improvements. Each bar on the chart represents 1 month of energy. The red part represents gas consumption, the blue part represents electricity consumption, and for the calendar year 2006 I used a total of 80 gigajoules of energy, which was reasonably typical for the neighbourhood. And over the course of the next few years made significant improvements to the house, most of which you could think of as fixing the leaky bucket. And in 2011, disconnected from gas, further improvements, the result of which was 2013 consuming only 20 gigajoules of gas. So that's a 75% reduction in the gross consumption of energy by the house, and that remaining consumption is fully offset by the solar on the roof. So moving on, I want to look at the idea that wires beat pipes as a way of explaining the relative merits of electricity versus gas. Let's look at gas as an energy source. It involves combustion, giving heat and products of combustion, and in that it really is a one-trick pony. That's gas as an energy source, that's all it can do. Electronics, on the other hand, and the wires that deliver energy to them are effectively a solid state technology. There are no products of combustion. It's intrinsically simpler and more reliable and safe than combustion and pipes. An example of this is in the earth leakage safety switches that most houses have, and that's a capability that makes things safer, and it's not something that's directly possible in a gas system. Another key point is that electricity is extremely versatile because it can be used to carry both energy and information, and our society runs effectively on energy and information. Furthermore, electricity can be directly transformed to light and sound and heat and motion and stored chemical energy. And most of those processes are entirely reversible. And we can generate electricity at home from the sun. And using electricity as an energy source is fundamentally a much better fit with digital technology because they're both electric at the end of the day. So that means that we can more readily get smart features in an energy system based on electricity, and it's easier to meter. Lastly, electrical and electronic systems scale amazingly well, much better than gas systems, all the way from a pacemaker to a PV panel right up to a pumped hydro plant. The variations in scale are truly amazing. So next, the idea of low-grade energy versus high-grade energy is a useful one. High-grade energy is something that can give very high temperature differences or achieve high temperature differences. Examples are gas flames and electric arc furnaces. Low-grade energy, on the other hand, obviously low temperature differences. So if we're trying to heat a house, we might need something in the order of 25 degrees. If we want domestic hot water, we need 40 to 60 degrees. So in terms of bringing this to a discussion about efficiency, don't use high-grade energy when low-grade energy is sufficient. So why start with 1900 degrees when you only need 25? That's a sledgehammer to crack a nut. Remember Hawkins' idea of aligning with natural forces? Well, using gas flames to give you 25 degrees comfort is a sledgehammer to crack a nut. Now, wouldn't it be great if we had an abundant, free, low-grade heat energy source? Well, as it happens, we do. It's the ambient air and sometimes ambient water around us that holds heat energy. Let's explore that. In understanding ambient heat, it's useful to distinguish heat on the one hand from temperature on the other. To help understand that, think back to the leaky bucket analogy. The heat is analogous to the water in the bucket, and the temperature is analogous to the height of water in the bucket. Now, low-grade heat energy is all around us, and principally we can use air as a source of that energy. The heat energy in the outside air is effectively infinite and renewable. So that heat energy, it's like a fluid. It can move from one place to another. Heat naturally flows down the hill, where that hill is the temperature gradient from hot to cold. But with the right technology, we can force the heat up the hill, so to speak, from cold places to hot places. And the devices we use to do that are called heat pumps. Here's mine. This is a split system at my house, and it uses a small amount of electrical energy to move a large amount of heat energy. It extracts that heat energy from the outside air and brings it inside. So in terms of efficiency thinking, you don't need your mains energy supply to be your source of heat when low-grade heat is needed. So Hawken will be happy. I think heat pumps represent a great idea of aligning with natural forces in extracting low-grade heat out of the outside air. Next, a tale of two grids. A modern urban society has two parallel energy grids, electricity and gas. They effectively represent separate silos of energy, and we don't really get good value for having two separate ones. It's not like they give us any useful fail-safe redundancy. And as I explained with electricity, using that electricity makes gas increasingly redundant as an energy source, as we can do most of the things that people use gas for better with electricity. And if we were perhaps to only have an electricity grid, then the societal cost savings would be immense. So zero carbon is an economic proposition, or this helps the idea of zero carbon as an economic proposition, because we can have a lower cost energy system without gas. For example, homes that are all electric have only a single daily service charge and one energy account. So with an all-electric energy supply, the role of the electricity grid changes. So in houses with significant amounts of electricity generation, the role of the grid shifts from being a supply system where customers only consume energy to being a sharing system where customers produce and consume. So that mind shift from supply to sharing is fundamental. Next, I want to talk about the idea of diversification of energy. So this helps explain how the electricity grid can cope with more different types of uses. So if we displace gas and displace petrol by using electricity, there is hope for us to be able to cope with that increased amount of energy use by increased diversification. So there is diversity in the pattern and timing of energy use. And where diversity is increased, we can get better utilization of that existing asset. And we can use smart management technology to help keep within the operating limits of the system. So diversified loads, and diversified generation, and a common energy transport, we're much better off. So, for example, or a specific example of diversification is the consumption that comes from electric vehicle charging would typically have a different pattern and timing compared with the pattern and timing of normal home electricity consumption. So because those patterns aren't then completely additive, we don't end up having twice as much load on the grid as we would if those patterns lined up. So to bring this to a close, is it economic? Yes, electrification, I think, represents aligning with natural forces. And I'll make the case here with a specific case study. The case study is replacing gas ducted heating system, a home's existing gas ducted heating system with a heat pump. So this is a replacement scenario, and in this scenario the system being replaced is a gas ducted system with a burner efficiency of 70%, and it's represented by these flows on the chart. So you can see from the left we've got a significant amount of gas energy coming in, 33 megajoules, to deliver 10 megajoules of heat. So this scenario is looking at the heat flows the energy flows associated with delivering 10 megajoules of useful heat into a house. So for that 10 megajoules useful into the house, 33 megajoules of gas, some energy for the fan, and a bunch of heat flows or energy flows associated with waste heat, waste delivered heat, duct losses and flue losses. So overall we've got an end-to-end efficiency of only about 29%. Let's compare that with a heat pump system using a split system, an affordable, common and well understood technology. Now for the same 10 megajoules of delivered heat, we only need 2.3 megajoules of electricity, a little bit of energy for the fan, and most of the heat required for the process is coming from the outside air. There's still a little bit of losses along the way, but overall you're talking functional efficiency of 391% versus 29%. So that's about a factor of 13 difference. So if, for argument's sake, we say that the per megajoule cost of gas is half the price of electricity, then we're still using it in the order of 4 to 6 times less cost for the same amount of delivered heat with electricity as compared to gas. So overall, the efficient electric scenario is much better, and in the case of the split system, we get heating thrown in effectively for nothing. Sorry, we get cooling thrown in effectively for nothing. So let's have a war on waste energy, electrify our energy system, plug the leaky buckets and get heat pumps. Thanks very much.